I'll warn you in advance. I warned my other class that my son's here. He's playing Minecraft. What's it called? RL mod. And apparently it's really hard. So if he yells out, he might yell out some expletives, just warning you in advance. So anyway, he's 13 and he's always cussing in front of his dad.
Yeah, I know some complicated mods too, but anyway, there's a bunch of like railcraft, astronomy, etc., etc.
Yeah.
Okay. Yeah.
Cool.
I sometimes play Minecraft with a bunch of other complicated mods. Anyway, I know it's in like other like in Calc 1 and in like physics there's equation sheets for the class and the final. Is there one for this course too?
Well, so normally yes. The catch is, let's see, is that in the summer you guys are lucky and you can just use the book. So
we can use the book for even the final?
Yes. Yeah.
So wait, the finals open, so the entire finals open book?
That's right. Yeah. If that's okay. You guys cool with
I'm not used to this. This is kind of weird.
Yeah, don't actually get used to it, because when you take Calc 3 and like DiffyQ and stuff in the fall, if you do, or in the fall or spring, you probably won't have that capability. I think it's just one of these things that it's, I don't know, maybe I'm just being too nice. But once in a while I get a nice streak. And so in the book, I think if you go past the index at the end, it doesn't quite have all of the stuff. Normally in the test you would be given, maybe I can just shrink this down a little bit. You would be given this sheet, so that's differentiation and integration rules. On the next sheet is all of the trig stuff, all the identities and definitions and stuff. On the next one, you know, if you need it to remember, like, okay, yeah, what's the formula for that? So there's that. But then the next, no, not the next page, that's a bunch of algebra stuff. Here we go. So on this page, it's got all of the,
I don't know if you're sharing anything.
Ah, god dang it. Yeah. Okay, repeat. So if you go to the end, does you see it now?
Yeah.
Okay. So if you go to past the index at the very end, you've got the derivative and integral rules there. So that's where that is. All the trig stuff is on the next page. All of the sort of basic area volume stuff, if you need it. I'm not sure you will, but you can use that. There's a few things on algebra, you know, exponents and factoring and things like that. Then the next page has all of those formulas for summations. The trapezoidal rule is there. We didn't do the error formula, but the error formula is there. Simpson's rules right there in condensed form. They don't use H's, but they use the function values. And then another error estimation. And some of these other things that we're going to see along the way.
All right.
Yeah, so you can just use those. And of course, in the section, as we're working through this stuff in numerical integration, it's got a nice, reasonable box. If you don't want to switch to that, it's here. Key idea 5.5.1 has the formulas, but again, you still have to like interpret what all this stuff. How do you get delta x, and how? You know, it says it here. Here's all the heights. There's the 42424 thing like that. So
just not necessarily knowing what equation word for word, but knowing how to use it and how to get each part of it.
Yeah, that way I can make the problems on the test a lot harder because you now have all the formulas.
Lucky us.
Yeah, lucky you. No, we'll see. We'll see how that goes. So no big curveballs on these things. So anyway, how about, do you have any specific homework questions?
That's it from me.
Okay. All right.
I have one homework question, but it's actually on yesterday's homework because I didn't get a chance to ask you about it.
Sure.
Okay, so last night's homework, not last night, it's for the night before last night. On problem number 35, I understood how to do B and C, but I didn't understand how to do A or what A was asking for exactly. I just didn't understand exactly what it was asking for.
Okay, so repeat that. There was section, which section, which problem?
5.3, problem 35.
All right.
I didn't exactly understand what it was asking for
Okay.
from A. Define a formula to approximate B and A f of x, or the integral of f and x.
Okay. Did we do this last time? I think we might have.
Yeah, you did, but you did, but I don't think I was there at the moment.
Okay. So we are trying to do this integral, and you start off by using the right-hand points.
Yeah.
Okay. Now, we already know the answer to this problem, because if we then shift to section 5.4 and just use fundamental theorem, we just take the antiderivative of this, we get x to the 4th over 4, plug in the endpoints, evaluate those, and subtract, we get a quarter. We know the answer is a quarter.
Yeah, that's the derivative, antiderivative in this instance.
That's right, yeah. But we're doing these problems just because they're good practice, they're not too difficult, we know what the answer is, but we're practicing the method. So that not only can we do this in 5.3, but you just saw in 5.5, we wanted to expand the method to trapezoid rule and Simpson's rule. And if you look on Wikipedia, it'll say Riemann, trapezoid, Simpson, level 1. And then you have these things called Newton-Cotes formulas, which will go like level 2, 3, 4, 5, get much more complicated formulas, better approximations, but much more complicated formulas. So if you were going to program a computer to do this, you probably wouldn't use Riemann. You use one of these fancy ones. So it doesn't stop at Simpsons. But anyway, just again, for practice, you want to take the interval from 0 to 1, and you want to chop it into n pieces. So these are like, I don't know how many there are, but there's lots of them, potentially lots of them. You do it into n pieces here. And then if you did that, then the overall width, or the delta x, would be the entire width, which is 1, into n pieces. So it's like 1 over n, 2 over n, 3 over n, 4 over n, 5 over n, all the way across. So that's the width. The x's themselves, x1 would be 1 over n, because I would start at 0 and I would go over 1 point. Then to get to the second one, I would go over 2 widths. So my second x point is 2 of those widths. Or you can write it as 2 times 1 over n, or just 2 over n. It doesn't matter. And then the third point would be 3 of those widths. And you will keep going until you get to the last point, which is n of those, which should make sense, because if I did n times 1 over n, the n's would cancel and I would get 1, which is exactly where I would end up at the very end. So these are all the n values, and I'm using the right-hand point, so I want to go to the right of the first one, the right of the second one, the right of the third. So those are all of your pieces for that. So if I did a Riemann sum on this to get a formula, what would that look like? Well, I'd have to find the heights of these things. So height 1 would be, I'd put them into the function y equals x squared, or cubed, y equals x cubed. So the first height is just the first y value, which I get by plugging the first x value into my function. So I would get 1 over n cubed. And then the second height would be 2 copies of 1 over n cubed. And the third height would be 3 copies of 1 over n cubed. And I go all the way across until I get to n copies of 1 over n cubed. So those are all of the heights in that. And now if we use the Riemann approach, the area of all of the rectangles here would be width 1, or the width, times the first height. And then I'd have the width times the second height, and I'd add that on. And I'd do the width times the third height, and I'd add that on, and all the way across. Now we've already seen in the formula it's not a bad idea to just factor out the width from all of them. It's going to have this width of 1 over n on every single piece, so I don't want to rewrite it over and over and over. And what's inside here is the first height, which is 1 over n cubed, the second height, which is 2 times 1 over n cubed, the third height, which is 3 times 1 over n cubed, all the way across to n copies of 1 over n cubed. And that's my answer for adding up all of these rectangles, but not in a very condensed form, because this dot means continue to add. And if n was 1,000,000, I'd have 1,000,000 terms there, and I don't really want to have to add up 1,000,000 terms. So I need to condense this somehow. So if you can see that this is width 1, or the width times height 1, the width times height 2, the width times height 3, all of those are area 1, area 2, area 3 of all of the rectangles. So how do I make this nicer? Well, I noticed that I could write this as 1 over n cubed. I could write the next one as 2 cubed times 1 over n cubed. The next one I could write as 3 cubed times 1 over n cubed. So I'm just using this property that you can take a product to a power and then just apply the power to all the stuff. So 2 cubed, 1 cubed, n cubed, and I get this. 3 cubed, 1 cubed, n cubed, and I get this. And I keep going all the way across until I get n cubed 1 over n cubed, like that. Now, okay, great. But now I also notice that every single one of these terms has a factor of n cubed. So I factor again. I factor here, 1 over n. Inside of this first set of brackets, I factor out 1 over n cubed. And if I do that, this first one is 1, and technically it's 1 cubed, which doesn't matter, but it'll help me with my pattern recognition. I write that as 1 cubed because the next one is 2 cubed, and the next one is 3 cubed, and all the way across, I get n cubed. And now I'm like, oh, I've seen that pattern before, where if I have something cubed plus something cubed plus the next thing cubed plus the next cube, and I stop at this point, the formula that I gave, I didn't derive this one, is that I can condense that. So this is 1 over n, this is 1 over n cubed, and then all that stuff in the parentheses can be condensed down into n times n plus 1 all over 2 squared, like that. So that's just the formula for the sum of cubes stopping at n will give me this formula right here. So that's a super nice condensed formula. I can plug in 1 billion now, and I just have to put in 1 billion in 4 places on my calculator as opposed to having to add up 1 billion things. Just because I don't have a lot of space here, maybe we can do this. If we were to square all this stuff out, this would be n squared. This would be n plus 1 squared. That would be n squared, n plus 1 squared. This would be 4. So I'm squaring everything. And now this together, those would be n to the 4th. So let's see, I would have n to the 4th on the bottom. I've got n squared on the top. So I could cancel 2 of the n's out, and I would be left with n squared on the bottom. I cancel that with these 2. I still have n squared on the bottom. What else do I have? I still have a multiple of 4 on the bottom, and I still have n plus 1 squared on the top. So all of that is part A for your problem. And so I think your question was on part A. Kyle, is that right?
Yeah, it was. I'm just kind of looking at this a bit because it's a little So starting from the beginning, exactly how exactly does x1 equal 1 over n instead of just equaling 0 because it starts with 0?
I'm using the right hand points.
Okay, that's right.
So on that, on that little tiny interval right there, the left point is 0, but the right point is 1 over n. So I use the right.
Okay.
Point. Yeah.
Oh, okay. This makes a lot more sense. Okay, I understand it.
Okay. Yeah, I mean, it's a lot of algebra. It's a lot of pattern recognition, knowing what the heights are, putting all these pieces in, factoring properly. This is like honestly one of the more complicated things you're going to do in the entire class. Trying to do all this sort of symbol chasing.
I mean, when I was in the problem, I felt like I was on this course, but I was thinking maybe I was doing way too much work than was required because I had that problem with some of the other problems previously in this section. So I was just want to make sure.
Yeah, definitely. But now that if you can get this for part A, part B is really easy because all I got to do is for the first part of part B is I just plug in 10. So if I plug in 10, I'll get 100 and I'll get 11 squared over 4 times 10 squared. So that'll be 121 over 400. And that would be my approximation for the first one. For the second one, I'd want to put in 100, so I'd get 101 squared over 4 times 100 squared. So maybe that's a lot bigger. I don't know how to rattle that off in my head, but you could do that. But if you put in bigger and bigger and bigger and bigger and bigger numbers, like if you put in a huge number, this whole thing is going to be super close to just 0.25, which is a quarter, which is exactly what I already knew the answer was if I used section 5.4.
Okay.
Could you please explain the concept in number 27 from the 5.4 homework?
Yeah. 5.4.
Because it says the answer is 0, and I don't understand that.
Okay, so well, there's two things you can do on this. One, just draw the picture. So you're like, is there a picture? And the answer is, well, yeah, sort of. If you said, the curve is y equals 0. So that's the x-axis. So if I just tried to do this, then the function is right there. That's really thick line there, but that's y equals 0. And then I want to do this between -2 and 2. What's the area that you see there? And the answer is, I don't see any area because there's no height to it. And so basically the width is 4, but the height is 0.
That makes sense. Thank you.
The other thing is if you wanted to say, well, what function do I take the derivative of to give 0? So you have to take the integral of 0 dx. And the answer is, well, 0, but it could be plus c. So really, your answer could be any whole number that you wanted it to be. So if I'd said, well, according to this, I'd have to go f of 2 minus f of minus 2. But no matter what value I plug into the function, I just get c. So this would be like plus c, and then this would be plus c. But what happens when I subtract c minus c? I still get 0.
That helps. Thank you.
Sir, what about 25? There was no constant number on it, or there was no.
Yes, 25. That's a sneaky one, because it just looks like this. And you're like, where's the function?
Yes, sir.
Function's supposed to be right there. So we hid it from you. What function could I put in there to make that equal the same? The answer is just 1. Those are the same.
Wait.
Because if I multiply 1 times anything, I get that thing. So it's 1 times dx, I just get dx. So I've kind of hidden this function in there. The function is just 1.
I got it.
Yeah, so what happens when you try to find the antiderivative of 1? The answer is it's x.
That'll be 0, right?
Right, because well, let's see. Yeah, it would be, no, it wouldn't be 0. Because let's draw the picture now. Try again. Because the picture says draw the function y equals 1. So here's 1. between -4 and 4. So this is the x-axis. This is my curve. I want the area under the curve. So what is that area? It's just a rectangle.
Oh, so it's 1 times 4, right? No,
Well, how far is it from here to here?
that's 8.
Correct. So that's 8. That's 1. And so the answer better be 8.
Got it.
Now, and I think you did exactly what lots of people do. You integrate and your function is x. It's right here. My function is x when I integrate. So I need f of 4 minus f of minus 4. Just plug in the bounds. So if I plug in 4, I get 4, because it's just x. If I plug in -4, I get -4, and you're like, that's 0. And the answer is, careful, it's you subtract them.
So, yeah, okay. I see.
Or
Because
minus-
-7
minus.
times -4.
Yeah, which is it. Yeah.
I've got a few that I'm stuck on. I've got 31, 33, and then the last 4.
Also, I'm just curious, is class over now, or are we still going?
Well, it technically runs till 11:45, but if you don't have any questions on homework, you can peel out.
Okay. All right,
Okay.
great. Thank you.
Right. Okay. So, right. So some of these things, unfortunately, we try and cram. We honestly, even though it's summer school and there's extra time, we cram way too much stuff into this class. So some of this stuff gets a little bit by the wayside. So 31, we didn't quite get a chance to cover, but let's talk about it here. So we have this thing here, which is x squared. Here's 4. Here's 2. And we have the area that's under the curve here. So, what is that area under that curve? Well, we did the fundamental theorem here. We would get my antiderivative would be x cubed over 3. That's my function, capital F. When I plug in the bounds, I would get 2 cubed over 3, which is 8 over 3. F of 2 minus f of 0. And if I plug in 0, I'd get 0. So the answer is that the area under here is 8/3. Now, what the mean value theorem says is that area actually could be represented as a rectangle. If I just put in a rectangle, thing is what rectangle would I put in there so that is also of area 8/3. And so if this is 2, then what would the height need to be in order to get an area of 8/3? So I want this value here. So when I multiply 2 times whatever, I get 8/3. And I think that you can see probably that answer is 4/3. So that means that this height has to be 4/3. Now, the mean value theorem says that value 4/3 can be gotten as some value of your actual function. So I could have just stopped at a certain point and I would get the same area, like this area over here could be moved down. And they use the letter C. I want to find a value C so that C squared is equal to 4/3. I think that's what it says, yeah. So the answer here as well. I can take the square root of 4/3. And the answer to the problem is equal to this. And why you would ever want to do that, this is kind of related to the average value of a function, but and that's what we use it for. But for right now, the point is you get an area, it's messy, and those are bad. So can we do this as an area where it's just a rectangle? And the answer is yes. And not only that, we can do it with our function. by finding a specific point in the middle that would give you the same area as you would have there. So it's kind of like if you put that in water, dropped it, and it filled in a tank, what height would that tank need to be to get the same amount of water? And the answer is 4/3, which would have come by taking your point and going over to square root of 4/3 and going up to the function and then squaring it all off. So there's a lot of theory in there. We did kind of skip it. I don't think we're going to have anything on the test about it. It's mostly just maybe trying to read and interpret. So not very satisfying, but there's that. So that's 31. Was there another one like that?
It was 33, but I think I could figure it out.
Okay, yeah. 33, same thing. Find the area, find the height, and then back out what that value is going to be. So it's pretty similar to that. The last
And then my
one,
other ones were 51, 53, 55, and 57. I started them and I couldn't figure it out.
oh, 50, 53?
51 through 57, they were the odd ones.
Okay, so 51 is find the area inside of a particular region. So what this one looked like, it said draw x squared, draw 2x, draw 5x, and draw x equals 3. And if you do that, it'll make a region here. So this is 3. Y equals 2x is a slanted line, and this is also a slanted line. This one I know is steeper, so it's going to come up here to 15. Like that. And then this one, if I plug in 3, I'm going to be at 6. So that's that. So if I draw, here's y equals 5x, here's y equals 2x, and here's 3. So we're talking about that area right there. So we want to find the area of that region. So the area formula for this is you take the integral from the bounds, in this case that's from 0 to 3. That's the x values that enclose the region. And then I want to take the curve that's the high curve, which would be 5x. That's like the top one. And I subtract off the lower one. So that's the integral from 0 to 3 of 3x. And then I have to do the antiderivative. So I get 3x squared over 2. So I integrate that. So I plug in 3, and then I plug in 0, and I'll subtract. When I plug in 3, it'll be 3 times 3 squared, so that's 27. 3 times 9, 27 halves. And then when I plug in 0, I just get 0. So the answer is 27 over 2 for that area. Now, turns out actually, if I turn this triangle sideways like this, so that this is the side over here, you can do any triangle by doing 1/2 base times height, even if it's kind of this funky shape. So I know that this height here is 3 because that's the height here. So I've turned it sideways, but that's 3. The base is that value right there. So if I go from 6 to 15, that's 9. If I come down here, that's 9. So if I did 1/2 base times height, that would be 1/2 base, which is 9, times height, which is 3. And I do get 27 over 2. We don't usually do it where the height's like outside of the triangle, but you can still do it. It's kind of a crazy thing for any triangle that works. But setting it up is draw the picture, figure out what the region looks like, and then the formula for area is just you take the bigger curve and subtract the smaller curve and then integrate. Does that make sense? Okay. The last ones, I kind of, honestly just want to skip. They're not going to be on the test. They're just kind of put in there to complete the subject. You can blame Colonel Harold. She's the coordinator of this class, so she likes to make sure we cover everything. It's like a huge stickler for this stuff. But anyway, in general, and this is what I said at the very beginning, if you have a function which is the integral from a to x of a little function, that's the integral. If you take the derivative of an integral, you get the exact same thing back. And so that's the fundamental theorem of calculus part 1. Now, where it gets complicated is what happens if you create a function which also has another function inside of it. So it's like a to the x squared of some function in there. And you want to take the derivative of that. Well, now we got to go back to Calc 1, and there's this thing called the chain rule, which says if I take the derivative of a function, well, I can still use this, and it's still f of x squared, but now the chain rule says I got to multiply by the derivative of the inside, and technically x squared is on the inside, so I have to multiply by 2x to get it. And it's ugly, and we don't do a lot with it, and you're like, what's going on? But it is a chain rule, and now we have a function that's in an integral, and it's inside of the integral. It's just kind of a mess. But the procedure, say on 55, is the same thing. It's the integral from 2 to x cubed plus 1 of 1 over t dt. Then the derivative, according to the fundamental theorem of calculus, that's going on. Fundamental theorem of calculus, TC, part 1, is going to say the answer is 1 over x cubed plus 1. I just put whatever's there directly in. The catch is that in order to do this properly, the chain rule says, you didn't put in x, you have a different function is on the inside, so you have to tack on the chain on that, which is the derivative of x cubed plus x, which is 3x squared plus 1. So you get the fundamental theorem for this, and then the chain rule for that. And so that's how you do 55. Of course, then was 50, I can't remember, was 56 one of them, or what was the next one? What was the next one?
57.
Just 57, yeah. 57. Now you're like, wait a second, that's even meaner, because now I have two pieces in there. That's not very nice. So how do I deal with that? I only can deal with it if the x is at the top, because that's the only thing my formula can do. So I first have to do this trick where I put in 0 in the middle. I can put any number I want in the middle, but I put that in the middle. So if I go from 0 to x squared, then I want to get from x to x squared, then I have to put in x to 0. So I know that this is one of the properties where I can go to get from x to x squared, I can first go from x to a number, and then from that number to x squared, and then I can put them together to get back over to here. And that at least helps me with this one, but it doesn't quite help me with this one because the x is on the bottom. So what I need to do is get the x up to the top, and this is using another property which says that if I wanted to reverse the order of these things, I can, except whenever you reverse the order of the bounds, it reverses the sign of the overall answer. And so now I get down to here is what my function is. And I haven't done any derivatives yet. I've just rewrote it so that I can use the fundamental theorem, and it looks like probably a chain rule on that one there. So if I take the derivative of that, so fundamental theorem of calculus part 1 plus the chain rule would say, all I do is put the function in, so x squared minus 2, that's fundamental part. And then the chain says I got to multiply by the derivative of the inside, and here's technically the inside, and so I got to multiply by 2x. Minus, I use the fundamental theorem on this one, part 1. I don't have to worry about chain rule because it's just straight up x. This would be x minus 2. I'll just plug the x directly in. Derivative of the integral is the function, and I'm done. If you did want to use a chain rule, you could multiply by the derivative of the inside, but then the derivative of x is just 1, and therefore we get down to here. And so it's ugly. I suppose we could multiply this out to clean it up, but that's kind of as good as you, it's certainly as good as I would want to go.
So the last three weren't really stuff that we were going to go over, and it's not going to be on any test or anything.
No, that's right. Yeah.
Okay.
I mean, for a full, like,
All right.
calculate, like if you took this class at, take any math classes at another school, they often will be much more rigorous on abstractness, these like really like following all of the specific rules. We're an applied department. We skip proofs. We skip a little bit of the abstract stuff. Maybe, this is kind of stuff that people end up going to grad school eventually, which, sometimes people do. You may revisit this sort of stuff, but at that point, you probably would forget everything anyway, and then have to go back and review it. So we kind of leave this out. But for a complete sense, if this is fundamental theorem part 2, well, what's part 1? Well, this is part 1.
Okay. Thank you.
Yeah. I have to ask, Mohammed, do you watch soccer at all, English Premier League?
Yes, sir, I do.
Okay, so you probably know Mohammed Salah.
I do, sir.
I saw your name, and well, first of all, my middle son hates Liverpool, but
Well, I hate them too, sir. I'm a Chelsea fan.
oh, Chelsea, okay, yeah, they're playing. They're playing City right next.
Yes, we're playing them, and if City draw or lose against us, Liverpool is champion.
That's right. Yeah. So my son doesn't like Liverpool, but he loves Salah, especially when he plays for Egypt. The dude is a beast. He's awesome.
He is, sir.
Yeah.
He's crazy good.
Okay. So yeah, Chelsea. I mean, Pulisic, man, he's the man, right?
Not yet. He has a lot.
Hazard. I'll give you Hazard.
As I came to Madrid.
What?
As I went to Madrid.
When?
I think it was 2 summers ago.
No. Really? Eden Hazard. Isn't he? Yeah, I'm behind the times. Yeah.
I've been a fan of Chelsea since Drogba's days.
Oh, yeah, I love Didier. I miss him. I miss some of the old guys like him. I miss, well, certainly Beckham.
Beckham was Manchester. Lampard.
Yeah. I mean, just in general. I mean, he, of course, then he came over and played for the LA Galaxy for a while. Which
that was great though. He put MLS on the map.
That's right. Yeah, definitely. So, anyway, very cool. Yeah, I root for Chelsea too over City.
Thank you, sir. Hopefully we win.
Good luck.
Sir, I have a question about number 29.
Okay.
I didn't really get the question, so I had trouble explaining it.
Okay. So here's the deal: is anytime you have an integral, like before we get to 29, anytime you have an integral where it's like the integral from a to a of any function will always be 0 because there's no width. There's no area because there's no width. Now, anytime you have a function where you have a bunch of stuff down here and you have a bunch of stuff up here, if this area and this area are the same, then your answer will be 0. Because anything below is negative, anything above is positive, and they'll cancel each other out.
Got it.
So in 29, that's exactly what's happening. If you have an odd function and you draw it, then anything that you have, first of all, it has to go through the origin. Odd functions have to go through the origin. And if it looked like this on this side, then it would have to look exactly like that mirror on the other side. And the area here and the area here, at least if you go from the same point, minus a up to a, the answer for your integral will be 0 because they'll cancel each other out. And that's exactly, if you have x to the n and n is odd, then this will be an odd function and you'll get something like this and the answer will always be 0. If you go from the same point, negative on, from the negative to the positive, same value. If it's
Got it.
even, then that means, it doesn't have to go through the origin, but if I had a function that looked like this, then it would have to be exactly replicated on the other side. So if I went from minus a to a, on this side, I get the exact same area as on that side. So if I just double that, 2 times that, just 2 times the right side, it would be the same as if I did them together, because this is just a duplicate copy of what's on the right. And so that's kind of part B.
Okay, I think I got it.
Okay, yeah. All right. So yeah, minus 1 to 1 of an even function would be the same thing as I go 0 to 1 of an even function. I've got this side over here, and if I want to get it all, I would just multiply by 2 and I'd get the whole
Thank you, sir.
answer. Okay. All right, good luck.